Yeah, I'm delighted to give the first talk of this workshop. And as she introduced, I'm going to talk about the form, which is a symbolic manipulation system. And here, in these links, you can find the form website and also source code. Then Ben Roy and Jos Framasteren and I released the version for the 4.2 recently, and we uploaded to the release note paper to the archive. Here the number. And Jos Framasteren is the original author of the form. So in this talk, first, I'll go for introduction with physics background. And then I will discuss about the form, especially about the design principle. And then lastly, I will discuss about the form version 4.2. So what is a form? So as I said, form is a toolkit for symbolic manipulation or formula manipulations. That means it uses a symbolic computation instead of a numerical computation of using the floating real numbers. So as this is, so that this is just an example. So we just keep everything symbolic instead of the numerical calculation. And the form has been used in many theoretical particle physics computations, although the form is not restricted to any specific field of science or engineering. So why do we need symbolic computations? Because, well, it's exact. That's actually important in some cases. And if you have a symbolic result, then it may contain more information about the mathematical structure of the problem. So it would be difficult to see from numbers, it's difficult to see the original structure of the mathematics. And another thing is actually the theory is described in mathematics, so it's intrinsically symbolic. So let me go for a bit of detail about the theoretical physics for a while. So the researchers for the phenomenology, particle phenomenology, uses a framework of quantum field theory. So in this context, actually, if a theorist says some theory or model, it means Lagrangian. This quantity or object contains everything, so all information about the theory. And for example, quantum electrodynamics, which describes the interaction of between the electron in matter and the photon, which is the quanta of light, described in this Lagrangian. And there's a photon term and the electron, and also some interaction is involved here. Well, if you don't have any idea about this equation, please just enjoy the beautifulness of the equation, because beautifulness or simplicity is very important, I think, for theorists. So if you look at the Large Hadron Collider, then the nuclear force or strong interactions are very important. For this, we have a quantum dynamics, in which the Lagrangian is given by like this. So here, it's similar to the quantum electrodynamics, but actually it's a bit involved in many aspects. And if you go for the standard model of particle physics, well, the Lagrangian is described or represented in the Lagrangian in this photo. And it actually contains many particles and interactions. So now you have some beautiful theory. The next thing is some theory prediction. You want to make some theory prediction and compare with the experimental data to see whether or not your theory is realized in the nature. So just as an example, I want to consider some amplitude or some kind of probability of electron propagating from some point to another point, which may have some quantum effect. And the textbook of quantum field theory says, okay, you can just write down this quantity by some formula. And the point is that here is the input. So it's Lagrangian for your theory. So what you need is actually compute this object. Unfortunately, it's difficult. So one thing we can do is if the theory contains some small parameter, then you can consider a perturbative expansion about that small constant, or a small parameter. In the QED, actually QED has a coupling, which is the strength of the interaction, which is denoted by alpha, and this is less than 1. So that means that this series expansion may converge and may be a good approximation. So we want to compute this coefficient of the expansions. Now, how can we do that? Draw Feynman diagrams invented by the Richard Feynman. So just prepare or draw some line with arrow or wavy line, which means freely propagating electron and photon, and also interaction vertex of them, which is proportional to the square root of alpha. Now, you can consider or draw all topologically possible combination of them. Like this is one example, which contains the two vertices. That means it contributes to the order of the alpha. Then you can think more about such a diagrammatic expansion. Here, the number of the loops of these diagrams gives the order of alpha. So the one loop gives the alpha, and the two loops gives the alpha squared, and so on. And each diagram can be translated to some mathematical expressions by using some rules. But okay, so we can compute such an expansion. But in practice, it's not so easy. Because first, there would be many diagrams. So if you go for the higher order, higher number of the loops, or if you consider some more complicated processes, reactions, which may involve many particles, and also for example, the standard model, which contains many particles. So then there are many combinations of such a diagram. So it could be a huge number, possibly, let's say, 1 million or more. Another difficulty comes from actually, actually they have a complicated structure. So for example, if I want to compute this diagram, then it contains some kind of object, which is it's a bit complicated object. And if I naively expand this object, then it gives over 2 million terms. So it's a huge number. And last but least, it's actually divergent. So it's some kind of multidimensional integral contains divergence. And actually, from one loop, actually it's a divergent. So that means it's not easy to directly apply some numerical method. So instead of them, you need to first identify the divergence. Then you need to keep the divergence as some symbolic parameter. And after summing up all diagrams, then such a divergences should be cancelled or removed by some inconsistent way. Now, so what I wanted to say is actually, yes, we need a symbolic manipulation with for big computations, big expressions with many terms. And actually, what we need is just a basic algebraic operations like expansions or some addition or multiplication or sometimes some replacement with pattern matching. So we don't need any fancy automatic integration, very nice algorithm or knowledge of special function. And actually, the expression size could be very large. So in our applications, it reached to 2 terabytes of the disk space. So the question would be, which computer algebra systems can be suited? In the market, there are many computer algebra systems or symbolic manipulation systems. And yes, I would say about something about the form. The next. Okay, so the design principle of form. I think the most of computer algebra systems uses a tree structure to represent such expressions. For example, this expression can be represented as a tree of the using the node for the operator and operands. Well, I think this is a very elegant solution, and you can use some recursive algorithm for that. But if you consider the symbolic manipulation with big expressions, then maybe if the expression cannot fit in the memory, physical memory, then the operator system begins to use virtual memory. So it may give the random access for such a virtual memory, may give the very terrible heavy swappings of disks. So if your machine starts swappings, it's a game over. In the case of form, actually form always expands the expression like this. And form just stores these terms, the sequence of term, and just store as a sequence of sorted terms. And each term is relatively short, and it has complete information. And form allows you to 2 types of the operations. One is the local operations, which is applied to the each term. And another one is some special operations like global operations, like sorting of terms. So what does it mean? Form works as follows. So from the input, which may be in the memory or memory space or maybe disk space, form reads one term. Then this one term, for this one term, set of local operations are applied. Because it has a complete information, they actually, well, we can just, form can process this local operation without any reference to the other data. And they go to the sorting system. After that, form can read another term, and it can be processed in a similar way. And form repeats this process until the all terms in the input is processed. Then the sorting system of the form can use the external merge sort. That is good for even for the disk space. So in the end, what we need is just sequential access to the disks. So it would work with the disks. Another advantage of this structure is actually you can easily parallelize this program. So we use the master worker model. So from the input, okay, the master distributes the term into the workers. And because they are independent terms, so worker can process this. And in the end, the worker does the sorting, partial sorting. And then such a data is gathered to the master. And it performs the final sorting and writes the output. So actually, we have T-form, which is a threaded version using a POSIX thread, and PAR-form, which uses a MPI. As a programming language, I would say, well, form is using some style of imperative programming and using the term rewriting system. So you just write operations which will be applied for every term. So this ID statement, ID is abbreviation of the identify, which performs a replacement like this. And this question mark means that it's a wild card. So actually, it matches to the x to n, where n is any integer, and it replaced to the by the expression. That means just the derivative of x. Another notable feature of form is, I think, it has a very powerful preprocessor. It's okay, too powerful and maybe a bit tricky. But for example, you can define some code of block of code as a procedure using some parameters. So it's actually repeating this line n times. So you can define the mth derivative of x with the parameterized x and m. And then you can use a call instruction. Then this is expanded here. So I will show some concrete example. It's just a simple one. So the first line is just the definition of the ordering. Then form uses strict typing. So you need to say the A and B are symbols. And the third line, which defines the expression named f. Then just print and end. Then saving this text as example.frm, and then you can run the form from the terminal. It gives some output, and as I said, the expression is always expanded. Another example. So so here is just declining the symbols, and they find the f and some replacement, and here I put dot sort, which means if there is a dot sort, then form first read this text, then compile it into some internal code, and then run this part. Then so they are these replacements are applied, which may give some many terms, but then after the dot sort, they are sorted, and some terms would be cancelled. So in this sense, the user have full control of the sorting. After the run of the first block, form now compiles this part and then run this part. I just put some manipulations multiplying the some A over B with some condition. But anyway, I can get that result. Okay, thank you. 10 minutes. Okay. Well, and okay, so well, I have not so much time, and I think that my most important mission is to finish this on time. So I will skip this one. But anyway, the phone has many physics applications. If I use inspired search, then it hits the phone version 4 has over 1,000 citations. Sorry, this is version 3, and this is version 4. Version 4 has about 200 citations. And well, here I just mentioned the keyword of our recent works, which is forcer and author. And well, then I will talk about it, so I will skip. But they were actually the driving force of the development of the phone version 4.2. So how many minutes? Okay, thank you. So anyway, so this is just history. So phone 4.1 has been released in the 2012, and 4.1 appeared in the 13, and 4.2 is appeared in the we released in this July. And actually, the version 4.2 contains more than 20 new features and more than 50 bug fixes. And form is now well, okay, it's hosted on GitHub, and it's nice. It has nice issue tracker and wiki, and the repository is connected to some third-party services, which is for the keeping the quality of code. And actually, for the release of the version 4.2, we used the automatic deployment to this GitHub release page. And we are quite happy with such an automated system. Now, I want to discuss one application using the new features, which would be the graph manipulation, because the forcer and author, such a program uses the graph manipulation. Yeah, note that our first input was the Feynman diagram, so the graph manipulation is mandatory. So for the simplicity, I just discuss undirected graph, and okay, here the external line is labeled by Q, and the internal edges are labeled P1, P2, and etc. This can be expressed in form as follows. So I just declared a commutative and symmetric function Vx, and these labels are declared as vectors, and then this can be stored as an expression where which is a product of the Vx, where the Vx has these connected edges as an argument. And this is the same for the second vertex. Now, question. So, are they equivalent graphs? It's a bit difficult to see, but then, yeah, form can do that. So it's a bit, maybe it's a bit hard to explain, but here the first one is the first graph, and the second expression is for the second graph. And I just copy this structure to here with replacing, for example, P1 to Q1 question marks. So it becomes a pattern with wildcards. That means if there's this matches, then it actually keeps all connection of the vertices and edges. So it's equivalent. If I run this program, actually I can get, yes, this is equivalent, and I can get the isomorphic mapping. And another thing is ID all option in the ID statement, which is introduced in the version 4.2. It generates all matches, not only one, but it gives the sum of the all matches. So if I apply this graph with the all option, it gives this 4 term, which actually shows the Z2 times Z2 symmetry of this graph, which is a horizontal flip and a vertical flip. But okay, they are nice, but actually I just wrote these patterns directly in the source code. This may be not so nice. So the patterns should be, well, for now, rather static and fixed. Maybe there would be some better way. And actually, yes, you can do that using some creative use of features. So one is a dictionary feature which is introduced in version 4.2, which actually aims some text replacement, like mu1 should be a LaTeX form, for example, for the output. But the point is, this is also applied to the expansion of the preprocessor variables. So, okay, I don't go for details of this explanation, but the point is the expression is stored in this variable, and when this variable is expanded, they actually, by using the textual replacement of the P1 to Q1 question mark, for example, it gives what we needed. There's another method, which is actually replacement of this pattern or the left-hand side of the ID statement at runtime. So actually, it contains some P1 or P2 or such things, but then you can replace it dynamically by the wildcard, and it gives this pattern. So it brings me to my conclusion. So form is designed for symbolic manipulation of very big expressions with many terms, which is required by the theory prediction of the perturbative quantum field theory. And actually, form has been used in many cutting-edge computations. And we added new features in form 4.2, and we hope that it helps users to make ever smarter programs, maybe by using some creative combination of the features or some abusing them of them. Okay, yeah, that's all. Thank you. Yeah, thank you.
Now, I think that technical challenges that you were reporting might be interesting also for computer scientists. Wondering how many of your team are actually physicists and how many are decided to talk to computer scientists about these things?
Well, if I talk about the form, actually, well, form developers are actually physicists, but we are Actually, I think Ben Ryle will talk about the HepGame project, which is actually using the phone, but it also contains some members from the computing science. Yes.
Now, given that artists are sort of dying when it comes to, terabyte storage, we all need heavily SSDs for terabyte storage, and I guess soon we'll even use RAM or semi-extensive RAM for this. Do you think that basing such technology on sequential access is still the way to go?
Well, I think, I'm not so sure, but I think if you consider that, for example, cache coherency, then even for the memory or SSD, maybe the sequential access is better than the random access, I guess.
Hi. I saw in the new features of forms that you had something about spectators. I've
Yes.
tried to guess what they could be
Well,
for the rest of the
spectators,
talk, but couldn't.
well, yeah, so that one. How can I say?
Perhaps it's not easy to explain.
Well, actually it's some temporal storage to store some so-called spectators of the expressions. So if you apply some operations, then maybe the sum of your expression, or sum of terms, would be not affected by some such a local operation. So it doesn't give anything, but it's needed to the processed anyway. So it may be slow down the program. So you can somehow move some part of the expression to another buffer or actually file. This is the spectator files. Is it okay?
Okay, so that's to sort of take parts of the expression and say, well, you know that you're not going to do anything on them in this stage.
Yeah.
Okay, thank you.